what is 5.1? 5.1 is on exponential function. Basic exponential functions has the pattern y equals to, let me see, our textbook use A or B for the base. I think they usually use B, but let me make sure. They use B, okay. Because SMC textbook use A as the base, so I will use B to the X, where the B, the base has to be positive and cannot be 1. If we try to imagine that on a number line, so it has to be greater than 0, not including 0. It has to be greater than 0, okay, but avoiding 1. Okay, from 0 to 1, not including 1, and then from 1 to infinity. Okay, that's where the base should be. Now, I will explain later on why the base cannot be 0, the base cannot be 1, and the base cannot be negative. For now, we just take it by faith that the base has to be positive and not equals to 1. The first thing, we do example, what an exponential function look like. Example 1, the standard exponential function is y equals to 2 to the x. What I want you to do, try to work it out, construct a table for that y equals to 2 to the x. We want to plot this. So if this is x, this is y. When x equals to 0, what's the y? X equals to 1, x equals to 2, x equals to negative 1, x equals to negative 2. Find the y's.
One, 2, 4, 1 over 2.
1, 2, 4,
1 over
1/2, 1/4, right? Okay, so yes, that's right. So what I think I will try to do is I will try my best to follow the grid here. 0, 1, that's the Y-intercept. And then 1, 2, 1, 2 approximately here. 2, 4 approximately here. Negative 1, 1/2. Negative 2, 1/4. You will see when I try to connect the dots, we will have this equation. When I connect the dots. Now you can expect when x equals to 3, the y will be 8. And on the left-hand side, I keep on going very, very close to the x-axis, but you will see it will not be touching x-axis. Now, you will see some phenomena if you have the base 2 to the x. The phenomena is the following. When x equals to 0, the y is 1. Notice that when I move 1 unit to the right, let me use this color here. When I move 1 unit to the right, I double whatever I have earlier. I double it. When I move another 1 unit to the right, I double whatever I have here. Do you see that? So when x equals to 0, the y is 1. When x equals to 0, the y is 1. When I increase the x becomes 1, the y is being doubled. When I increase the x by 1 unit, the y is being doubled. When I increase the x again by another 1 unit, the y being doubled again. Now that's because the base is 2. Which means every 1 unit I move to the right, I multiply the previous value by 2. Multiply the previous value by 2. Now, because when I move to the right 1 unit implies I multiply the value by 2, then what happens if I go to the left 1 unit?
Half.
I multiply by 1/2. Okay, so you see that from here, I'm 1, y equals to 1, it becomes 1/2 multiplied by 1/2, 1/4, 1/8, and so on and so forth. Okay, now notice that as long as the y value is positive, when we move to the left 1 unit, we keep on dividing by 2. Okay, a positive number divided by 2 will still be positive. Is it right?
Mhm.
Okay, so that's why the magnitude, the value will get smaller and smaller, but it will never touch 0. Okay, it will never touch 0. So let's summarize what we have here. You have seen this supposed to be in your intermediate algebra, but I want to summarize that again. First, the y-intercept is 0, 1. Second, the domain is all real number. How about the range? From this graph you see,
0 to infinity.
including 0 now?
Include. No, don't include it. Don't include it.
Not included. Okay, and then we have horizontal asymptote. That will be y equals to 0. Now, this horizontal asymptote is only one side asymptote. To be more precise, the notation should be as x approaching negative infinity, the y will approach 0. However, as x goes to positive infinity, what happened to the y?
Goes to infinity.
It goes to infinity also. So you see that this horizontal asymptote is a one-side asymptote, okay, not two-side asymptote. Furthermore, we see that the base, because the base, which is in this case is 2, as long as the base is greater than 1, then the graph is increasing. Okay, now those are the important summary we have. And I would like you to also have these 3 important coordinates keep in mind. Okay. I will explain to you why I call these 3 coordinates important. Basically, when we have exponential function, the graph will turn the sharpest basically at these 3 points. Okay, you will see that to the left of these, it tends to be quite not that steep. It's kind of like quite linear already. And the one here, even though it's still increasing, but it's not as steep. I'm not sure. I cannot say it's not as steep. How to say? When it bends, the bend actually happens the most around these 3 coordinates here. Okay, so we will use these 3 coordinates as part of our framework. Use these 3 coordinates to help in graphing. Okay, now let me ask you to kind of like fill the sketch. Try to do a little sketch for example, y equals to, let's say 3 to the x. Now, I want you to do it the same way I did earlier. Yeah, like example 1. Okay, now once you kind of like get the rough sketch, you get the rough sketch, I want you to do this summary too. This summary here, I want you to do this summary. Okay, you will see, you're supposed to see exactly the same thing. Okay, let me give you like 5 minutes to do that. Okay, let's start. So my x will be 0, 1, 2, and then -1, -2. The y will be 1, 3, 9, 1/3, 1/9. Is that right? You
Yes.
can put more if you like. And then the graph will be, I actually don't need such a big one. Well, anyway, 0, 1, let's say it's approximately here, 1, 3, approximately here, 2, 9 is very far up there, -1, 1/3, -1, 1/3. So the graph is approximately like this. And you'll see that first the y-intercept is 0, 1, still the same, right? By the way, we can actually say more besides the y-intercept. We also have 1, 3 and -1, 1/3. Is that right? Okay, those 3 important coordinates, remember? This guy, and this guy. Second, the domain is all real numbers, while the range is from 0 to infinity. Okay, and then horizontal asymptote, that's y equals to 0. And part 5, because the base is greater than 1, then the function is increasing. Okay, now let me ask you to take a look on this my graphing software. I will compare these two basic exponential function. Y equals to 2 to the x looks like this, while y equals to 3 to the x like this. Now I hope, you know what, let me copy paste this thing. The reason I want to show you that here is because of the following. Now, this guy here is y equals to 2 to the x. Well, this guy here is y. I'm sorry, it's the other way around. It's the other way around. The other way around. This is y equals to 3 to the x. This is y equals to 2 to the x. Now, they intersect at 0, 1, the y-intercept. Okay, but from that point on, 3 to the x goes to infinity faster. It actually grows faster compared to y equals to 2 to the x. Okay, so you see the larger the base, the faster it goes to infinity. Okay, and strangely, because the base is larger, then it actually dies down. It goes to x-intercept faster too. You see what I mean? As if the following, as if it is the following. The greater the base, the faster it escapes to infinity. And the faster it converges, approaches horizontal asymptote. Okay, you can see the one here. This is the higher exponent, right? I mean, the base is higher. Okay, because the base is higher, it goes to infinity faster, but it also goes to the horizontal asymptote faster. Okay. Now, the similarity between these two graphs is that both of them has base greater than 1. Let's do further comparison. What happens if the base is less between 0 to 1? What happens if the base is between 0 to 1? Let's say I use 1/2 to the x, 0.5 to the x. You will see because the base is between 0 to 1, then the graph is actually decreasing. Go back here, let me put some notation. This is y equals to 3 to the x, and this is y equals to 2 to the x. The graph here is y equals to 1/2 to the x. Notice that if the base is between 0 to 1, then the graph is decreasing. Strangely, all the information we had earlier stay the same. For example, the y-intercept is still 1, 0, 1. Okay, this is the y-intercept here, right? The y-intercept still 0, 1. In fact, the other two coordinates still follow the same pattern. 1, comma, the base, -1, comma, 1 over the base. In this case, that's 1, comma 1/2, -1, comma 2. 1, comma 1/2, -1, comma 2. These are three important coordinates. Going back, the domain is still all real numbers. the range is still 0 to infinity. And then we have horizontal asymptote, y equals to 0. But notice that the horizontal asymptote is only on the right-hand side. Okay, as x approaching infinity, the y approaches 0. When x approach negative infinity, the y approaches infinity. Okay, and this is point number 5, that if the base is between 0 to 1, then the graph is decreasing. Now you see, if you compare this notation, this summary to the one we have above, the difference is only at part 5. Give me a second. Yeah, the difference is only part 5. It's either the function is increasing or decreasing. Oh, by the way, we can actually do this y equals to 1/2 to the x from a slightly different point of view. You can see this as 2 to the power of negative x. Let's see this way. Let's see this way. That's equals to 2 to the negative 1 to the x, right? Which is 2 to the negative x. Which is basically the graph of 2 to the x. That's the graph of 2 to the x reflected with respect to y-axis. If you remember, we replaced 2 to the x here replaced by negative x. Right? And when we do that, we reflect with respect to y-axis. Now, from here we see something very important. And what we that tells us what we are going to do with this. So what to do with these graphs? Okay, the first one, we will use the fact that the graphs are either increasing or decreasing, and therefore the function is, I wonder if you remember, if the graph is increasing or decreasing, then the functions are one-to-one. Now, we talked about this quite long time ago. When did we talk about this? We talked about this at section 3.5 when we talk about inverse function. Now, if a function is increasing or decreasing, then the functions is one-to-one. Because the function is one-to-one, then there are two consequences. First, we will use this to solve equation. Second, there we are anticipating the inverse function. Inverse of exponential functions. Okay, now the second thing we will do with this graph, which I think I will do after the break, is transformation. Yeah, for example, later on we will learn to graph the function f(x) equals to 2 to the x plus 3 minus, let's say, 4. What the graph look like. Okay, and the domain, the range, horizontal asymptote, x-intercept, y-intercept, so on and so forth. Okay, now what I will do now is I will do this part. I will do this right now, and after the break I will do this. While 1b is something we will see in 5.3. Okay, now how do we use that to solve equation? Basically the following. To solve equation, if we have b to the x equals to b to the y for b positive and not equals to 1, now that implies the exponent must be the same. Well, because exponential function is 1 to 1. Notice that we need that 1 to 1ness to solve the following question. Let's say a very simple example. For example, if I have 2 to the x equals to 2 cubed, by 1 to 1ness, x equals to 3. Okay, because 2 to the x is a 1 to 1 function. Notice that we cannot say the same thing if it is not 1 to 1. Let's say if I have x squared equals to 3 squared. X squared equals to 3 squared does not imply x equals to 3. In fact, to be more precise, you will see that x either equals to 3 or x equals to -3. Okay? And that's because x squared is not 1 to 1 function. Now, for exponential function, it's 1 to 1 function. So as long as the base the same, then the exponent must be the same. Okay. Now let's do some problems from the book. I picked questions from page 336, 334. Now, before I start working on that, let's remind ourselves some basic properties, basic exponential rules. Something you should have known. B to the x times b to the y equals to b to the sum. If we multiply the same base, we add the exponents. Let's say 3 to the 4 times 3 to the 7, that will be 3 to the 11. Okay. Second, the quotient rule, b to the x over b to the y, that is b to the x minus y. For example, if I have 10 to the pi plus 2 over 10 to the pi minus 2. That will be 10 to the pi plus 2 minus pi minus 2. That will be, the pi cancels, 10 to the 4. Okay, and then the third basic exponential rules is b to the x to the power of y is equal to b to the xy. So if we have, for example, square root of 2 to the power of square root of 2 to the power of square root of 2. Now you see, then I will multiply these two guys here. Okay, that will be square root of 2 to the power of square root of 2 times square root of 2, which will be square root of 2 to the power of
2.
2, which is
2.
Okay. Now, actually, I can continue on the last part here, that this also means b to the yx, which means I can write b to the y to the x. In other words, b to the x to the y, I can switch the order here. Okay, that's something nice to know. Now, with this knowledge, then we should be able to do questions, for example, number 12. Number 12, 2 to the x equals to 32. The way we solve this, you need to rewrite this 32 with base 2. That's 2 to what power?
5.
2 to the 5th. Because they have the same base, and the base is not negative, the base is not 1, then the exponent must be the same. Okay, that's for part A. Part B. 2 to the power of t equals to 1/4. So 1/4 is 1/2 squared, right? The reason is because 1/2 is 2 to the power negative 1. You see that? Okay. If you happen to see, if you happen to be able to jump from here right away to here, go for it. Okay, but I still need you to write this before then you say in the next line, by 1-to-1ness t equals to negative 2. Now part C, 2 to the power of 3y plus 1 equals to the square root of 2. Now, square root of 2 is 2 to what power?
The half.
Yeah, 2 to the 1/2. Now then from there, by 1-to-1ness, 3y plus 1 equals to 1/2. And then from there, you solve that as usual. Now, the harder one, part D. 8 to the power of z plus 1 equals to 32 square root of 2. Now, you need to see that this 8 as a base and 32 and 2 are all have common base 2. So I will write that 8 as 2 to the power of 3 to the power of c plus 1. The 32 will be
2 to the 5th.
2 to the 5th, and square root of 2 is 2 to the square root of 2 is 2 to what power?
Square root of 2?
2 to the 1/2.
Well, oh, I don't know what he's asking.
Okay, maybe I write it as a property there. The nth root of b is equals to b to the power of 1 over n. Okay, so then here I will get 2 to the power of 3c plus 3 equals to 2 to the power of 11 over 2 when I add 5 by 1/2. Now then by 1 to 1ness I get 3z plus 3 equals to 11 over 2, 3z equals to 5 over 2, z equals to 5 over 6. Okay, now let's take a break. Right now it's 5:35. We will come back at 5:45.
Hey, Professor.
We solve the basic functions. I mean, basic equation. Let's do slightly harder one. For example, number 40. For example, number 40. We have 4x squared times 2 to the x minus 9 times 2 to the x equals 0. I can factor 2 to the x. So I get 4x squared minus 9 equals to 0. Right? I can factor further. Now you see that either 2 to the x equals 0, or 2x plus 3 equals 0, or 2x minus 3 equals 0. Are you with me? Now the key is here. This one here will not apply. Why? Because 2 to the x is always greater than 0, can never be x equals to 0. Maybe think about the range of 2 to the x. It's from 0 to infinity, right? Never equals to 0. Okay? Now then I go on for this, I get x equals to negative 3/2, x equals to 3/2. So for this equation, we have only two solutions, this guy here and this guy here. Okay. Now, actually the rest of the problems here follow the same nature, the same idea, and therefore I will not go on with number 42. But let me give you another type of question. Consider this my type. For example, if I have 4 to the x and then minus 3 times 2 to the x minus 2 equals 0. How do we solve this? Notice that this is actually a quadratic-like equation. Notice that 4 to the x is 2 squared to the x, which is 2 to the x being squared. Therefore, if I say let u equals to 2 to the x, then the equation becomes u squared minus 3u minus 2 equals to 0. You know, let me make it plus here. Let me make it plus here. Okay, so I get u minus 2 times u minus 1 equals 0. So I get u equals to 2 or u equals to 1. 2 to the x equals to 2, x equals to 1. 2 to the x equals to 1. What will x be? You can see 1 as 2 to the 0, right? So x equals to 0. We will see this kind of question further later on. I think in 5.5, they put solving log and exponential equations in the same section. So at that time, we will spend more time on solving equation and inequality. But at least right now, you have a feeling already that when we solve exponential equation, we basically try to catch the same base. So what is new for us here is this. In this last example here, that's what we learned. Okay. Now, the variation from the beginning, that's basically seeing that as a quadratic-like equation. That's all. Okay, that's for solving equation. Simple equation, exponential equation. Let's go to the second part. Second important parts here is about graphing. Let's say, for example, I will graph. For example, I will graph fx equals to 2 to the x plus 3 minus 4. The way we think will be as the following. The basic function is the basic function is 2 to the x. Now, what do we do to the graph to make it 2 to the x plus 3?
We're going to bring the graph down 4 units.
No, that's if you subtract by 4. What if I replace the x by x plus 3? What happened to the graph? We move 4 or 3 units to the left. Now then, when I have 2 to the x plus 3 minus 4, then I move the graph down by 4 units. Okay? Now, with that said, then what's the domain? What is the domain of the original function of 2 to the x?
-3 to infinity.
The domain.
The x cannot be. The domain negative 3 to infinity.
The domain is?
-3 to infinity.
No. The domain for exponential function is all real numbers.
Oh, I thought you were talking about in this one right here.
Yeah, but even this one, you will see that it's still all real numbers, because if the original domain is all real numbers, then after however you move it, it's still all real numbers.
Oh, okay.
Okay, now how about the range?
I have no idea.
Yeah, the range originally is from 0 to infinity, right?
Yes.
When you move to the left 3 units, the range still the same.
Yeah.
Now, when I move down, the range becomes -4 to infinity. Now, then let me ask you to find the Y-intercept.
0,4.
4.
No. Oh, yeah, that's right. I'm sorry. I thought you said 0, -4. My bad.
No,
0,4, that's right. Because F0 equals to 2 to the power of 3 minus 4. That's 8 minus 4. That's 4. That's right. How about the X-intercept? You set the Y equals 0. Solve this equation.
1. 0, 1,0.
Mhm.
-1,0.
-1, 0. The X-intercept is -1, 0. How about the horizontal asymptote?
It'll be how much you moved it down.
Okay, so originally Y equals to 0. You move down 4, it becomes Y equals to
-4.
-4. Okay, now let's see if we try to graph this. Let's try to graph this. Oops, sorry, this is not good. Let's try to graph this. 0, 4, 0, 1, 2, 3, 4. And then -1, 0 is here. And then Y equals to -4. Y equals to -4. 1, 3, 4. So this is the horizontal asymptote. Yeah, that's the horizontal asymptote. The thing is, with only 2 coordinates is enough. It's not really enough for us to get a good feeling about the graph. So what I will do is I will use those 3 important coordinates. One of them is 0, 1. From 2 to the x, 0, 1. Move 3 units to the left, 1, 2, 3, and 4 units down, 1, 2, 3, 4. Okay, another one is 1, 2. Move 3 units to the left and 4 units down. And then -1, 1/2, 3 to the left, 4 down. 1, 2, 3. Let me erase those highlights so that we don't get too confused. So many things there, right? But you see my examples. I start with, I need to memorize those three important coordinates. Oops, ouch. I need to remember those three important coordinates. Okay, and then I move them according to the transformation, 3 units to the left, 4 units down. Now I have this point, this point, this point, this point, this point. Now connect them. Okay, so that's y equals to 2 to the x plus 3 minus 4. Okay, so in addition to the y-intercept, x-intercept, and 3 important coordinates. Okay, that's the sketch of the graph look like. Now I would like you to do one graphing. You try this. For example, let fx equals to, let's say, negative 2 to the x plus maybe minus 3 plus, what is good? Times 4, plus 4. Okay, you try. Find the domain, the range, y-intercept, x-intercept. And then horizontal asymptote. And then sketch the graph. Okay, let me give you 5 minutes, I guess, from here. Okay, let's start. How about the domain?
All real numbers.
That's all real numbers. How about the range? You see that the range for this part here is from 0 to infinity, right? Now then, when I include the negative, the range between will be, the range will be from
Real negative infinity.
negative infinity to 0.
0.
Right? Okay, now then what happens if I add 4?
Negative infinity to 4.
Negative infinity to 4, that's right. Okay, now part C, how about the y-intercept? This one I think is ugly. When x equals to 0, when f0 will be negative 2 to the negative 3 plus 4, that's negative of 1 over 8 plus 4. That will be 3.875. It's basically 3 and 7/8, right? 3 and 7/8, almost 4, but not 4. While the x-intercept, 0 equals to negative 2 to the x minus 3 plus 4. Let me move the negative term here to the left to make it positive terms. So I get 2 to the x minus 3 equals to 4, which is 2 squared. So x minus 3 equals to 2, x equals to 5. So the x-intercept is 5, 0. How about the horizontal asymptote? Now you will see the horizontal asymptote always the constant. Y equals to 4. Okay, now using those informations, then let me sketch the graph. Okay, now then, let's see. Horizontal asymptote first. Horizontal asymptote y equals to 4. And then the x-intercept is 5, 0. Yeah, 5, 0. And then the y-intercept is 0, 3.8 something. So it's almost like this. Huh? Okay, what else do we have? No more, huh? Okay, let's do the basic graph of 2 for 2 to the x. 2 to the x, the y-intercept is here, right? And then according to the transformation, what do I do? 3 units to the right. And then I make it upside down. And then up 4. 1, 2, 3, 4. I wonder if you can follow me. Yeah, originally 0, 1, right? Move 3 units to the right. And then upside down. And then move up 4. That's the transformation. Now, using the same idea for other coordinates, 1, 2, 3 units to the right, upside down, up 4. So it comes back here. And then negative 1, 1/2, move 3 units to the right, upside down, up 4. Okay, so you see then the graph will be something approximately like this. Okay, that's the graph of y equals to negative 2 to the x minus 3 plus 4. Okay, now let me go on. Let me go on to 5.2. Nothing really new with 5.2, at least the one that we can talk about at this point. For 5.2, that's actually a special case. where the base b is now e, which is approximately 2.71, let me see, 271,828. Or we can round it to, approximately 2.72. If you want to round even further, you can approximate that using 2.7. Okay. Now, this E is a special number. This E is a special number, but how the reason it is special, we can only see that much, much later. If you want to see the reason, you can read the book, of course. But there are many more reasons why this E becomes something special for us. Now, this E is actually an irrational number. In fact, we can call this transcendental number. Transcendental. One of the number transcendental constant that we learned before is pi. That's approximately 3.14. We can say this is your second transcendental number. That's approximately 2.72. Okay, 2.72. After we round it to two decimal places. Again, what's so important about this E, we can see much later. Actually, I prefer to say that we'll see that in calculus, or the earliest will be in 5.6, I think. I think it's the earliest will be 5.6 or 5.7. Right now, I will just see that as a constant 2.7, which means when I sketch the graph, if I sketch the graph, it will behave quite similar to 2 to the x. Okay. It's actually steeper than 2 to the x. It's steeper than 2 to the x, but less steep compared to 3 to the x. So the important coordinates will be 0, 1, 1, comma e, negative 1, comma 1 over e. Okay, and the horizontal asymptote will be the same for the graph of y equals to e to the x. Now, you can approximate this 1, comma e as 1, comma 2.7. You can approximate this as negative 1, comma 0.4. Approximate. Let me make sure. Yeah, approximately 0.4. Okay, now we will use these informations to help us going further in graphing. Suppose, for example, we want to graph y equals to negative e to the x minus 1 plus 1. Now, I want you to do this, do the same question we did earlier. First, the domain. Second, the range. And then the Y-intercept, the X-intercept, horizontal asymptote, and then the sketch of the graph. Now, on your calculator, I hope you have your calculator with you. Make sure you know how to find the E there, okay? Make sure you know how to find the E there. Otherwise, then you will use 2.72 in place of that E. Now, let me ask you to try this. You will see the domain and range. are actually the same to if you replace the e by 2. Okay, now let me ask you to do this in 5 minutes. The domain will be
All real numbers.
all real numbers. How about the range?
It's going to be negative infinity to 1.
Negative infinity to 1. Good. The y-intercept is a bit harder. So f0 equals to negative e to the negative 1 plus 1. That's approximately negative 0.4 plus 1. If I round it to 1 decimal place, is it right? That's e to the negative 1. This is e to the negative 1. Okay, if I round it to 1 decimal place, so that will be 0.6. So the y-intercept is rounded to 0, I'm sorry, yeah, 0, 0.6. Now, however, if I ask you to compute that using calculator, the 5 decimal places, what will that be? Do you know how to use your calculator to compute that?
Yeah. Let's go like, oh, here you go.
My calculator.
0.3, never
0
mind.
point.
0.36787 minus 1. Is
I mean, you mean 1 minus.
it 1 minus or? Oh, I did minus.
Yeah. Okay, so you will get 0.63212 if we round it to 5 decimal places. Okay, just make sure that you know how to use calculator. Okay, yeah, just make sure you know how to use calculator. Now, part D, how to find the x-intercept. So 0 equals to negative e to the x minus 1 plus 1. That's e to the x minus 1 equals to 1. But 1 is e to what power?
0.
Okay, so from there we get x minus 1 equals to 0, x equals to 1. So the x-intercept is then 1, 0. Okay, now using, how about the horizontal asymptote?
Horizontal asymptote at y equals 1.
Y equals 1, that's good. Okay, then let's see when I try to sketch the graph. I know graphing this e to the x thingy is kind of like something most of us don't like. I myself don't like it, but let's try it. Let's try it. There are things that we don't like, but we have to do anyway. Okay, the x-intercept is 1, 0, isn't it?
Mm-hmm.
Yeah, it's 1, 0. How about the y-intercept again? 0, 0.6 approximately, right? And then horizontal asymptote y equals to 1. Okay. What else? That's all we have, huh? Okay, let's do the 3 important coordinates thingy.
I have a question, please.
Melissa?
Yeah. The x-intercept you said is 1, 0.
The x-intercept is 1, 0 is here.
Okay.
Yeah, okay. Let's see now. E to the x looks like this. So the important coordinates are 0, 1. What will this 0, 1 doing if we do this transformation? The transformation is to the right 1 unit, and then reflect with respect to the x-axis, right? And then up 1 unit, is it right?
Yes.
So from here, I move 1 to the right, upside down, up 1. Oh, okay, that's 1, 0. How about this 1, E? 1, E. If I move 1 unit to the right, that's 2, E. Upside down, that's 2, negative E. And then I go up 1. That's 2, 1 minus E. So 2, negative 1.7 approximately. Here. And so on and so forth. So I believe the other point will be this one here. Then when I pull the coordinates, the lines, if I connect these points here, it will be approximately like this. Okay. I think you need to learn how to sketch the graph using the transformation, at least to those 3 important coordinates. Okay. And that's how I actually get these 3 coordinates here. Okay, I will leave it there for this 5.2 suggested homework. For 5.1 and 5.2 will be 5.2 first, suggested homework for 5.2. Don't do this until you are done with your test. So on Wednesday, after you're done with your test, then you start working on this. I would like you to do number 15, 17, and then 21 for 5.2. That's all I need you to have. And then for 5.1, or 5.1, you have a lot more that you need to do. Basically, number 3. Number 31, and then 39, 41. For this one here, just do every other odd if you feel comfortable with that. Okay, so that's for your suggested homework for 5.1 and 5.2. I still have approximately 25 minutes, so let me just go on to 5.3. I strongly suggest you to watch the lecture video that I already gave for my SMC. Now, let me show you what I'm talking about. Let's see. Did I show you that already?
No.
Not yet? Okay. Let's go to the browser. You see my browser right now?
Yes.
Okay, now you go to YouTube.
Oh, we go to your channel?
Yeah, go to my channel. Did you do that before?
Yeah, I did.
Okay. And then from here, go to Arduino. Okay, and then click my face or my name. Now you will go to playlist. Here, go to playlist. Now the reason I asked you to go there because SMC happened to be ahead of you. We get 2 weeks off basically. 1 week basically they suddenly give us a week off, and then they move our spring break, right? Now Santa Monica didn't give us a 1 week off, and basically the week after the week that we have a week off, they didn't have week off. They just go on with their class. Okay, so what happened is they're supposed to be 1 week behind you because they start 1 week after WLAC College. But because we have 2 weeks break, then they suddenly now 1 week ahead of you. You see what I mean?
Mhm.
Okay. Now, so for them, they already finished their chapters with exponential and logarithmic function. Now, for their textbook, their exponential and logarithmic function is actually starting from 4.2. So you see that their 4.2 and their 4.2 or 4.3 is basically our 5.1, 5.2. Okay, so if you watch their lecture video, I hope that helps enrich you. What I cover there is pretty much the same to what I cover here, except that their 4.2 and yeah, their 4.2 start to have some word problems that we will see in 5.5 or 5.6. I don't remember. Okay, so if you want to try to catch up, I need to go a bit faster with our class, and for that to happen, I need you to watch the lecture video, so that when I go over that with you, I can go even faster. Okay, yeah, they already finished 4.2, 4.3, 4.4, and 4.5. I wonder, I think I did 4.6 with them or not. I don't remember. Well, anyway, that's for the YouTube channel. Okay. Now, if you want to see yours, yours is here. Yours is, hold on. Yours is here. Yours is here. Okay, I did 4.4, 4.5, and then 4.6, 12.2 to 12.5 at that time. Okay, so then after today, I will post the one for 4.7 up to 5.1, 5.2, and 5.3. Okay, yeah, that's for the lecture video. I wonder why I'm missing one section. Anyway, let me go back to my tentatives, my notes. I go to 5.3. And for this 5.3, it is 5.3. It is logarithmic function. Now, of course, I cannot finish this section within 15-20 minutes, but at least I get you the very basic, something I really, really need you to have. What is that? Definition. Definition for the base greater than 0 and not equals to 1. So the base greater than 0 and not equals to 1, log base b of a equals to c. If you see that notation, it means it has the same meaning to b to the c equals a. Now, we usually say the left-hand side here as the logarithmic form, the log form. And the one on the right-hand side here, we call that exponential form. Okay. Now, throughout my career, I found out that we can solve a lot of problems by just knowing this conversion from log form to exponential form. Now, let's see, for example, Let me pick questions from the book. For example, if you take a look on page 357, number 9. The question is, write in log form. So they give us an equation in exponential form, and we need to rewrite that in log form. Part A, 9 equals to 3 squared. That's exponential form. What will the logarithmic form be?
Log
Mhm.
9.
What is the base?
3.
Base
3.
3, that's right, of
9.
9 equals to
2.
2. Now, when you have log, this position here is called the argument. This is called argument. Okay, while this 3 here, the same 3 there, we call that the base. What do you think we call the 2?
The exponent.
That's right, the exponent. Okay, so the guy inside the log is called the argument. Now let's do more. Let's do more. Part B, we have 1000 equals to 10 cubed. You do it. Part C, 7 cubed equals to 343. And part D, square root of 2 equals to 2 to the power of 1/2. Okay, how about part B? What is that in log form?
Log base 10 of
Log base 10 of
1,000
1,000
equals 3.
equals 3.
Yeah.
And then how about part C?
Log base 7
Mm-hmm.
of 343 equals 3.
Equals 3. That's right. How about part D?
Log base square root of 2.
Log base. Oh, no.
Oh,
Log
I'm
base
sorry.
2
Log base 2
of square root
square
of 2 is
half.
1/2. Okay, now that's writing in log form. Oh, you know what? Let me talk about some convention first. Convention. If you see log without any base of C, this means the base is 10. This means the base is 10. Okay, while if you see natural log of C, that's actually log with base E. Okay, that's just for notation. Just for notation. Something good to know. Even though I have to warn you ahead that if you use old textbook or if you deal with old instructors, assume that you transfer to UCLA or Berkeley later on, and your instructor happened to be somebody quite old, almost expired, then for older generation, older textbook, log without base C actually have the same meaning with natural log C in older textbook. Okay, now, while when they need to do base 10, they just write the base. You see what I mean? Now that could be confusing. That could be confusing. Like when they use base 10, they write the base. If they don't write the base, that's natural log. For our notation, a more modern notation, if you don't see the base, that's base 10. If it is base E, they will use natural log. Okay? You don't need to worry about this older textbook notation. Just be aware that if you read old textbook, that you may see that difference. Okay, the one we use is this one. This is the one we use right now. Okay, just to remind us. Let's go on further. How about number 11? Number 11. On the same page. This time we need to write in exponential form. Part A, log base 2 of 32 is 5. Now you do it, okay? Part B, write that in exponential form. Log base 10 of 1 is 0. Log base E of square root of E is 1/2. And part E, natural log of 1 over E is 1. So try to write them in exponential form. I wonder why I do number 9 and number 11. I should do different numbers. Yeah. No, that's okay. Okay, part A. The base is
Base is 2.
exponent
5,
equals to
32.
32. Part B, the base is
10,
exponent
0,
argument
1.
Okay. By the way, we may write this also as log 1 equals to 0. If you omit the base, that's base 10. And part C, this is the base is
Base is E,
exponent
half,
argument,
square root of E.
and finally
E to the negative 1 equals 1 over E.
okay, so that's how we change from exponential to log and log to exponential form. Now, why we need to learn that? At least it helps us to compute some basic or simple value of logarithmic. Let's say number 18. Number 18, log base 25 of 1 over 625. The question is evaluate this. And how do we compute this without calculator? The trick is you call this x first. Call this x first. Let's say log base 25 of 1 over 625 is x. Now then, change this into exponential form.
25 to the x
Equals
1 over 25.
1 over 625. Now,
625.
25 and 625 has common base
5.
5. Okay, so this is 5 squared to the x. And 625 is 5 to what?
I don't even know. The 4 or something?
That's right, 5 to the 4th. So 5 to the 2x equals to 5 to the negative 2. I'm sorry, negative 4. So by 1 to 1ness, exponential form, right? 2x equals to negative 4, x equals to negative 2. Now I go back now. So log base 25 of 1 over 625 is negative 2. Okay, that's for 18a. How about, let me go ahead with 18, let's do 18b first. I believe I have enough time. 18b log base 16 of 1 over 64. Let's call this y now. You can use x if you want, but let me call that y for now. Let me give you 2 minutes to work this out. Pull it to the right. So this will be 16 to the y equals to 64. The common base is
4.
So 4 squared to the y equals to 4 cubed. So 4 to the 2y equals to 4 cubed. So by 1 to 1ness, 2y equals to 3, y equals to 3 halves. So,
Why is it not 1 over 64?
Oh, yeah, that's right. My bad. My bad. Thank you. So this is 1 over 64, next negative 3, negative 3, negative here, negative here. Is it right now?
Yeah.
Okay, so log base 16 of, thank you. 1 over 64 equals to negative 3 halves.
So,
Uh-huh.
64 is 4 square too. Not 12.
Yeah, 16 equals to 4 squared.
Yeah, but 64.
6 what?
Oh, okay, fine.
Okay, now finally the last one, part C. Part D, let me just go ahead to part D. Part D, log base 2 of 8 radical 2. Let me call that K for now. Therefore, 2 to the K equals to 8 times square root of 2. 2 to the K is 2 cubed times 2 to the 1 half. Right? So 2 to the K equals to 2 to the 7 half. So 3 plus 1 half is 7 half. Right? Now then from there we see K equals to 7 half or 3.5. So log base 2 of 8 radical 2 equals to 7 over 2. Okay. Now, my suggested homework, your suggested homework from here will be suggested homework for this 5.3a, because I will continue on next Tuesday, next week. Number 9, number 11, and then number 17. It's quite basic, but I need you to be able to do those. Okay, now let's see. What do we do on Thursday?